Hello friends, welcome to ML with AP. This is the video 2 of the series of video where we are discussing decision tree. We are discussing both the classification and regression use cases. Let's move on. So we have already discussed these things and we were at the point where we were discussing the unanswered questions, lot of questions, right? Now if you have not watched the first part of this video will not make that much sense to you. I highly recommend you to go ahead, pause this video and go ahead and watch that and come back over here. So few of the questions which we already answered in last video is that how do we build the tree? So we already know we build recursively, we build top down, and our loss function is entropy. Entropy is something which we are reducing, or information gain is something which we are maximizing. What should be my root node, right? So root node also we discussed in last video that all the features are candidate for to become the root node. We have to calculate the information gain for each of the candidates or features and then select the one where information gain or the reduction in entropy is maximum. How do we do the split? We do the split based on information gain or reduction in entropy. Now one question is left unanswered last time was how to build the subtrees. I know how to build the root node now, but how do we build subtrees? We'll see just in a minute. When to stop? When will I know that I have reached the leaf node? We have not answered that also, we'll see. What is the criteria to split the tree? Now we have seen that the criteria is very simple. Reduction in entropy or information gain, right? This is the criteria for a split. Now there is one more question that what if we have a continuous feature? What if my feature itself, like x1 or x2 or x3 or x4 or how many, one of them is not categorical, because in last example we have only seen categorical. What if the feature is continuous? Like instead of, let's say, age, which is old, young, adult, suppose we have the age as a number, which is 17 years, 34 years, 51 years, 79 years. What if it becomes a continuous feature? Then how do decision tree handles that? That is also a question which we are going to answer. If we have continuous output variable, so my y itself is continuous, what will happen then? Then it will become a regression. Whenever our output variable y is a continuous variable, that's a regression problem, right? But we'll see that how to deal with that in this particular video. Let's answer each question one by one. So how should we build the tree? Now we already know how to split the root node, right? Once we split the root node, we have to take a top-down approach and we have to build the subtrees recursively. What do you mean by recursively? That the same logic what we have applied for the root, same as you pick all the candidates, okay? By all the candidates mean all the features, and you try to see that which feature, if I split, will result in a maximum information gain or maximum reduction in entropy. That's how you split the base. Again, when you come to the child nodes, you take one child node as a tree itself, as a fresh tree you take, and then again for that particular subset of observations, you again start implementing the same logic which you have implemented to split the base node or the root node. And because in computer science we call this recursion, because we are copying the same logic, right? So think it like that we have written this function and we are calling that function recursively, right, to build the trees. I hope that makes sense, right? So my subtree, to build a subtree from a child node, you have to do exactly the same thing what you have done for the root node, and you have to keep doing till we hit the leaf node. And we'll see that when we have to stop, when we say that okay, this is a leaf node. We'll just see that in a minute. But how do we build the tree? This is the way we build the tree. Okay, so this is again, like if you see over here what I was saying just in a minute, if you split the root node, there are two child entries over here on the left side and the right side. You treat this particular subtree as a fresh node, as a fresh tree itself. But what will be the number of observations? The number of observations for this will not be equal to the total number, but whatever is falling under this particular left side. Suppose this left side was a yes, job yes category, right? So whatever observations are falling over here, job yes category, you have to treat that as your population and build another tree. Whatever tree you will build after that will become a subtree, and this is the whole point of having the recursion. When to stop? That's very important. We know how to build the tree, but how far we are going. So there are 4 important criteria, main criteria. There are many, but there are 4 main criteria. One is impurity or entropy becomes 0. When the entropy will become 0, when we'll have only one class present in a particular cell. In a particular node, if we have just positive class or negative class, in case of binary classification, if we have just a positive or negative class, that will become a pure node. That means entropy has fallen down to 0. Okay, when entropy has fallen down to 0, it's a pure class. There is no question of further splitting. What you will split? There is just one class, right? That's where you stop. There is another hyperparameter in this particular case, which is called max depth. Decision tree has a problem with overfitting. If you keep bifurcating, then that means you are keep writing if else then loop, right? Or logic. And you'll keep doing that till the individual one observation, right? And that's the problem where we'll encounter overfitting, right? So usually the hyperparameter is tied to a maximum depth, that how many, like 3 depth or 3 layer, how many layers of trees you are going to build. That means root, first subnode, second subnode, the node after that. This will be the depth. So what will be the depth of the tree? So in this particular case, this is the first, this is my second, right? This is my third level, this is my fourth level, right? So you have to see that how many levels or what will be the depth of the tree. If the depth of the tree has reached, you call that as a leaf node. Even if impurity is there, even if mixed classes are there, that's fine. You call that as otherwise overfitting problems will start. Impurity reached within the threshold. Suppose sometime you say that, okay, if my impurity or my entropy is like, let's say it's very, very minimal, right? It's 0 or very close to 0, 0.5, 0.02, 0.01, something, a very small number. I don't care after that, right? That entropy being 0.01 means that there, out of 100 observations in that particular bucket or cell, there is only one from another class, every 99 are from one class, right? So that's fine. Okay. Now total number of observation in a node is within the threshold. So sometimes we'll say that, okay, if the number of observation in a node itself has dropped into a minimum level, let's say 5 or something, I do not want to split it further down. It doesn't make sense to me to split it further down. So based on the number of observations, based on the impurity threshold, based on the maximum depth, and first thing is very obvious, which is that if the entropy itself becomes 0, that means if you have a pure node, one class, then you should stop. So friends, I hope you know that when to stop, and wherever you stop, you call that as a leaf node, right? That my tree, I have stopped building the tree further down. Now this is my leaf node. Okay. Now the second question was, what if we have categorical features with more than 2 categories, right? So we are only seeing yes, no. Let's say it's like one of the feature is something like cricket match or something, right? So there are 3 possibilities: win, loss, and tie or draw, whatever we want to call, right? Win, loss, or draw, let's say. There are 3 categories. What will do that? The answer is one hot encoding. If you know about one hot encoding, fine. Otherwise, I will just quickly try to tell you what one hot encoding. In this particular case, let's say this is our original data set. So it's very nice, 2 categories, right? Job is 2 categories, yes is 2 categories, my Y is also 2 categories, right? Let's say now my job is actually no, yes, and self-employed, 3 categories, right? So my feature, one of the feature has 3 categories. What will I do over there? What we do is we take this particular feature X1 and we map that, we create 3 new features out of it. Okay, 3 new features out of it. And this technique is called one hot encoding. What it means is that we are making this 3 category into 3 features which are each 2 category, 1 and 0. How we'll do that? Let's say if it is no, then one hot means out of all these 3, only one will be 1. Rest all 1 will be 1 means one feature will be 1. Rest all the 2 features will be 0. That's why the name is called one hot. That always in each of these rows, if you see, there is only one hot. Like you will find the occurrence of 1 only one time. Rest all will be 0, right? So this x1 is now morphed into 3 features: x3 no, x4 yes, and x5 self-employed. Whenever the no appears, I'll replace it with 1 0 0. That will be the encoding for no. For yes, the encoding is 0 1 0. Whenever x4 yes was there, I will put 1 hot. So only this bit will be hot, rest both will be cold, right? Similarly for self-employed, I will do 0 0 1. So self-employed, x5 self-employed will be hot, rest 2 will be cold, right? Now what we are achieving over here? We are achieving that from a multi-category problem, we have made 3 new features. We have added new features. That's fine, but still I can do my decision tree split over here on these features, on these made up features, because now it is only having the value 1 and 0, right? And if it is having only 2 categories, I can still implement my cart based decision tree algorithms, right? This is what you have to use one hot encoding to do more than 2 categories into a binary categorical problem. Okay, let's see. Question: can you think of a challenge with this approach? This approach looks very nice, but is there a challenge? There is one challenge over here. Did you notice that the number of features which we are adding is equal to the number of categories we have? Suppose we have a feature where we have 100 categories. Okay, it is possible that there could be 100 categories, right? Okay, let's say if it's month or something, there will be 12. Let's say if it's a customer segmentation, it could be many more. Now if there are 100 categories over here, that means we are adding 100 features over here, and we are increasing the feature. It will impact the model performance also. So that's the problem, and it will impact the performance also. That's the problem with this approach. So friends, next question is, what if we have a continuous feature instead of categorical? So see, in case of house, I have changed it with salary. Now salary is a number: 10 lakh, 11 lakh, 12 lakh, 30 lakh, 29 lakh, and it's a continuous variable. What if instead of a categorical, we have a continuous? So one question which will come to mind: how we'll do the split now? Because it was always yes and no, right? We were splitting 2 ways. How do we split now? Instead of yes, no, maybe also if there are 3, we have the mechanism of one hot encoding, and we used to do. But this is a continuous feature. What is the mechanism to do the split, right? That's the important question. Most of the principle what we employ with our categorical features remain the same. The only change which will happen over here is that we'll still calculate the entropy, the reduction in entropy, we'll still do the max information gain. In case of this, what we need to do is we need to arrange this in ascending order. So all these observations, let's say we are doing a split at the base, right, at the root node, we'll arrange this particular row or all the observations based on ascending order of this, right? Once we have got the ascending order of this, what we'll do is we'll treat the midpoint. Let's say my first observation is 5, okay, and the second observation is 10. The midpoint of 5 and 10 is 7.5. So my first candidate for H2 feature will be, should I split at 7.5, like salary less than 7.5 and salary more than 7.5? That will be my first candidate. My second candidate will be the net salary is 11. So what will be the midpoint of 10 and 11? 10.5. Similarly, my second split will be, should the salary be less than 10.5 and more than 10.5? And again, I calculate the entropy, I calculate information gain, everything in the same way, right? And there will be a candidate for X1 also, similarly for my categorical feature, yes and no reasons, yes and no split. But over here, in case of continuous, one of the disadvantages will be, in case of categorical, it is just one split. For each candidate feature, there is one split. But over here, the split is equal to, almost equal to the number of observations. If we are taking the midpoint, then it will be one less. Let's say we have 15 observations. How many midpoints of the numbers will get? 14, correct? So there will be a 14 candidate split. That means 14 times you have to evaluate, okay, these splits. And you have to also do the evaluation for job, which will be one split. And out of all these 15, you analyze that where I am getting the maximum information gain or maximum reduction in entropy, that particular split I should choose at my root node. And then again, similarly, you have to build the tree. That's the only difference when it comes to instead of categorical, we have a feature which is numerical or continuous. Okay, please ignore this maximum loan account. This is for the next slide, but please ignore this. Just treat this as that loan approved, yes or no. We are still dealing with classification setting and not with regression setting. So this is still yes or no, right? Okay, let's move on. Do you see any challenge with the continuous feature? I already told, because the number of combinations which you have to try is almost equal to the number of observations which you have, which is huge. If the observations runs into 10,000s or 1 million observations, you cannot, it will be very difficult and slow for the decision tree to run that number of combinations. And at each tree level, you have to subsequently run that many combinations, right? I hope you are getting that. So that's the disadvantage. Now, the next question is, what if we have a continuous output variable y instead of a categorical? Okay, which is the same thing over here. What if we have a continuous? So this becomes a regression problem, right? So that is called decision tree regression. Let's see how that works. So this is this is my decision tree regression data set. So my features are categorical again, but instead of loan approved y or n, I have a continuous variable. So next day prediction maximum loan amount. What is the maximum loan amount which can be approved? So next time a prediction can happen that, hey, if my job is this, my house is this, what is the prediction for you that what will be the maximum loan amount I can get approved, right? So this is a regression problem where the output y variable is a continuous numerical variable. Okay. Over here also, most of the principle remains the same except for one. Instead of entropy was good with the categorical, but how can we calculate entropy for continuous features? We'll not be able to. What we calculate instead is variance. So if you recall your statistics, I also have a series in statistics. If you want to see, you can see that. What we do is we calculate the variance at each level. Instead of entropy, same methodology, instead of entropy, we are calculating the variance or the reduction in variance this time instead of reduction in entropy. And we still call it the information gain. Okay. So formula for, just a refresher, formula for your variance will be what? You calculate the mean of the population. So mean will be like you sum everything up divided by 15 will be the mean, right? And for individual observations minus mean, you square it. You square the difference from the mean for each of these observations and then divide by big N. Big N is nothing but 15 in this particular case. This is the variance, right? So what you do is you calculate the variance, right? So the variance at the root node will be 192, variance at the root node. For the other split, again you have the candidate splits, right? So 192, 192. Again you calculate the variance for each of the splits. Okay, so we have two features categorical. We'll do two candidate splits. The variance in case of left split was 238 and 61. In case of right, it is 261 and 63. Very similar to how we were calculating entropy. Only the formula is changed. Instead of entropy, we are calculating variance. Again, here we were calculating reduction in entropy. Here we are calculating reduction in variance. If you notice, we are still doing this weighted, right? Because the number of observations which are falling in each category carries a weight with it, right? So we are calculating the weighted average, okay? And then we are calculating the reduction in variance. We'll still call this information gain. So information gain or reduction in variance in case of this particular split, it's 72. In case of this particular split, it's 49.8. Where I'm gaining maximum information? Over here. I will go with this particular split and not with this split. This is all how we arrive at the decision tree in a regression setting, right? Now, one thing one thing is to look at is that how do you do prediction? Now we have SciKit-Learn packages and all which will do the predictions, right? But intuitively, if you keep doing that with hand, if you are creating a decision tree, what will be how we'll do the prediction? Obviously, when some new features will come and you have to predict the variable, what you will do, you will go through the decision tree, right? Suppose if it's a binary classification problem, in this case you hit a node, if else then you keep doing that, right? And you from node to root to subtree to subtree to subtree, and you have hit a leaf. Let's say in that leaf there are 3 positive classes and 1 negative class. That's the leaf. There is no further subdivision in there. 3 positive class and 1 negative class. What will be the prediction? The prediction will be the majority class. That's how decision tree works. When you hit the node, you predict what is the majority class for that. That's it. Simple. In case of classification setting. In case of regression setting, suppose you hit the node. In regression setting, you will not get the classes like 3 positive, 1 negative. What you will get? You will get bunch of numbers. Like over here, maybe you will get 24, 12 and 60 in one leaf node, right? How you will predict what will be the value? The value of this will be the mean of this, the average of this. So the average of the leaf becomes my predicted variable. Hope it makes sense. Okay. Let's say one more last time, maybe like how this classification tree, what we are doing. Let's say we have 2 features and there were 2 class of problems, green and blue, right? Sorry, green and red. What we did with each of the split, we are either splitting across x1 or we are splitting across x2. So in a 2-dimensional space, we can easily represent it like this. So my first split, let's say, was x2 is equal to 60, less than or more than, right? So this becomes my first split. Similarly, we keep doing this split and my 2-dimensional feature space will look like this, right? So this is the mathematical intuition of classification tree. Like what we are doing is that we are doing the feature space and we are keep splitting this down till we meet a stopping criteria, okay? And after that, we'll do the prediction. So if my prediction is over here, in this particular, if it lands in this particular zone, obviously everything is red, so I'll predict red. Let's say if I land here, everything is red, I will predict red. Let's say for hypothetically, there was a mix of this. Suppose there are, in this particular case, suppose there are 7 greens and 3 reds, okay? We are not further subdividing it and we reach the leaf node. What will predict? We'll predict the majority class. Simple. In case of regression tree, again we are doing the same thing. We are building our decision boundaries, right? We are splitting across some decision, right? Here around 200, when x1 is equal to 20, we have another split, right? And since this is a continuous variable, how will predict the output or the prediction? The prediction will be nothing but the mean of this. So the mean of all these features become my prediction. The mean of all these features become my prediction. The mean of all these features become my prediction. That's it, right? Okay. I hope, friends, you got the very solid foundation of what decision tree classification and decision tree regression is there. Okay. Now there are certain advantages and certain disadvantages. I hope by now you already know what advantages and disadvantages is there, right? Let's try to see. What are the advantages? So explainability is very good, right? A decision tree, if you draw a decision tree, you can, if somebody, let's say in a loan situation, if a customer comes back to the bank that, hey, why did you deny me the loan? I'll put a case against you that you are you are not giving loan because I belong to a particular segment of the society or whatever, right? And you are doing something unfair to me. Now the bank manager can go, if he is using a decision tree, he can go and actually explain, looking at the decision tree, that okay, because you are falling in this leaf and you are meeting these criteria, because remember, decision tree is nothing but a giant if-else condition, right? That's why we have denied loan to you, and that's explainability. So if most of the models in machine learning are not explainable, so if you are able to explain and interpret the model, that's a good thing. Okay. Non-parametric in nature. Okay. So the other thing is that handles both categorical and numerical. We have seen that, right? So it can handle both the things. Require minimal data pre-processing. So if there are null values, if the values are at very different scale, you do not have to bring them all to same scale, do a standardization, normalization. You do not have to do those techniques, right? Decision tree is very robust in that way. Can be used for feature selection. We'll just see that in our code example. It can be used as a feature selection tool also, that which feature has the maximum impact on my prediction. You can find that through decision tree. Disadvantages. One of the serious disadvantages is that if you do not limit the depth of the tree, it has a tendency to overfit. It will keep digging down till you hit each leaf becomes one observation. It will keep hitting down till that level. It can be very sensitive to small changes in data. So let's say when you are doing the split, if a couple of observations has moved from very small changes in their y variable, right? Very small changes. But the split itself will change because of that, right? Because what you are doing is split. You are doing the split based on reduction in entropy or information gain. That is very sensitive to each individual observations, right? Limited to tree-like structures. Okay, so you can employ this into only these type of scenarios, right? Let's say you have to deal with text classification or video or images or something like that. Then decision tree is not the right tool for that, right? Not suitable for continuous output variables. Also, there is a regression use case which we have already seen just now, regression use case, but it is not very suitable for regression use cases, right? And the reason you know, right? Because what it is doing, it is not predicting. What it is doing, it is taking the mean of the whole class itself, like the whole block itself, right? Whole leaf, it will take the mean of that and then it will do its prediction, which is not very good, right? So these are some of the demerits also. Now with this being said, we have come to the end of the second video also. In the next video, we are going to see using SciKit-Learn Python package how to code decision tree right from the beginning. Okay. With that being said, I will close this video now. Thank you.